Hello everyone, today we are going to consider examples for section 4.2 subspaces. And basically I'll consider two examples, and we are going to check if they are making subspaces or not. Let's start with example number 1. Example number 1, I'm going to write down the question, okay? Are all matrices of the form A1, B1 making a subspace of M22. Well, in previous section we learned about spaces, right? In this section we are working with subspaces. Subspaces are actually parts, subsets of spaces which are like satisfying 10 axioms by themselves. And what is M22? It's a space of 2 by 2 matrices. And in lecture we kind of considered it and checked that it's going to work. So all matrices of 2 by 2 size square matrices are making a space. Now, well, some special matrices which have ones in the second column, are they making subspace? Like if we set up all possible matrices of this type, are they going to make a space in their turn? Well, if you remember in this section 2, we proved the theorem that to check whether subspace is really like a subspace or set as a subspace, we just need to check closure axioms. That's what we are going to do. Our closure axiom number 1 is addition, right? So if I take vector A1, B1, 1 and add another vector A2, 1, B2, 1, what I'm going to get? Standard addition operations is A1 plus A2, B1 plus B2, and here I'm going to have 2 and 2. Do you see that this matrix, because it has 2 and 2 here, does not belong to that subspace? So we already kind of checked that it's not a subspace. Sorry guys, pressed again, something wrong. It's not a subspace. We don't need to check anything else. You can also check multiplication. Multiplication is not going to work either, the closure under multiplication. Well, maybe you should check it just to show. Imagine that you take any number k and multiply by a1, b1. Remember that matrix multiplication by a scalar, it's ka, k1, kb, k1. So, well, k1 over here and k multiplied by 1 is actually going to be equal k. And if k is not equal to 1, then the result is going to be also that will not belong to the space. Will not belong to the space, does not belong to space. So they are not subspaces. So these matrices are not making actually subspace. There are other axioms which are violated, but well, when these two are violated, we don't really like care. We know for sure that it's not going to be a subspace. Okay? Example number 2. How about these vectors? All vectors of the form kind of similar, just the difference is zeros instead of ones, right? Are they making subspace of R4? R4 are all four-dimensional vectors. Are they making subspace? Well, let's check closure axioms. Number 1, A1, 0, B1, 0 plus A2, 0, B2, 0. And we are using standard addition for vector spaces. We are not inventing anything new. So A1 plus A2, 0 plus 0 is 0, b1 plus b2 and again 0. You see that we are getting the vector of the same shape, so it belongs to subspace. I don't know, I'm going to just label it w. Belongs to subspace. Very good. So we got a vector of the same shape. 6 multiplication by a scalar k, a0, b0. So, well, we multiplied by a scalar again. K, a. K by 0 is 0. K, b, and again 0. You see that the vector which we get as a result, this is just going to be a new number a, and this is going to be a new number b. I'm going to put tilde. So we have a tilde 0, b tilde 0, which also belongs to the same subspace, so same shape. So this is going to be a vector space. So here, yes. And the previous example, no. Sorry, instead of not, I was writing down non. Not, and this one is yes, it's a subspace. Okay, well, just remember closure axioms actually define whether it's subspace or not. If you see that other axioms were violated, you can always kind of try them, but okay. Okay, well, I think maybe I'm going to put spanning sets over here because this video is kind of short yet, just 6 minutes. So let me scroll it up and do over here spanning sets 4.3. So spanning sets, as you probably remember from the lecture, what is a span? Span is like a set of all possible linear combinations of a given set. Well, what is linear combination? Linear combination, it's like somebody gives you a set of vectors like S, V1, Vn, right? And linear combination, I'm going to label it as W. It's going to be K1, V1 plus Kn, Vn. So all possible linear combinations are going to produce like lots of these vectors W, and all these vectors W are going to be called span of this vector set. Well, we're going to maybe do first the next problem. I'm going to consider a set of four vectors. S consists out of V1, V2, V3, and V4. And I'm actually going to give their components. V1, 1, 2, 6, V2, 3, 4, 1, V3, 4, 3, 1, and V4, 3, 3, 1. So there are 4 vectors in 3-dimensional space. The question is, do they span R3? So what means a span R3? So actually, when you do a span of these vectors, is it going to cover all space of 3-dimensional vectors? So can you express actually any 3-dimensional vector as a linear combination of these 4? Well, let's write it down, how it's supposed to look. Let's imagine that we have any 3-dimensional vector W, and it's a linear combination of these 4 vectors. K1, 1, 2, 6, plus K2, 3, 4, 1, plus K3, 4, 3, 1, and plus K4, 3, 3, 1. So generally speaking, if we can express any vector in 3-dimensional space as a linear combination, if we'll be able to find actually such K1, K2, K3, K4, then yeah, it spans. Well, let's check it. Can we do it? What I'm going to do, guys, well, what we need to actually do, we need to multiply this k by each component and then add them together, and we are going to have W equals, well, I'm going to multiply k by 1, k1 by 1 plus k2 by 3 plus k3 by 4 plus k4 by 3, right? I'm just like combining first, multiplying k's inside and then combining x components. And I'm going to repeat it for all of them. So that's my first coordinate. And by the way, well, I don't know what are going to be the coordinates of vector w, but I'm going to just label them as w1, w2, and w3. Well, we see that this, to be able to kind of solve it for any vector w, we're supposed to have w1 be equal k1 by 1 plus k2 by 3 plus k3 by 4 plus k4 by 3, right? What's supposed to be w2? Well, actually y components, right? So it's k1 by 2, k2 by 4, k3 by 3, k4 by 3. And w3 is supposed to be k1 by 6, k2 by 1, k3 by 1, k4 by 1 again. Well, we have all the ones for 3. Guys, if you look at this, what is this? This is a system of linear equations, right? How many variables you have? Well, you have 4 variables, right? We have 4 variables here. How many equations we have? We have 3 equations, right? And what is like coefficients? Coefficients are actually going to be these components, and you can always write them down as column vectors, right? That's 1, 2, 6. And what is this? This is actually 1, 2, 6, and this is like multiplied by k1. And the components 3, 4, 3, 4, 1, and 4, 3, 1, and 3, 3, 1, like last 3 components. Well, this is, if it was homogeneous system, it would always have a solution because we have more variables than equations, right? But that's non-homogeneous system. Non-homogeneous means that we do have the right side. Well, generally speaking, we're supposed to solve it. Let's try. So what I'm going to do, guys, I'm going to like find the matrix of the coefficients, and that's going to be just the matrix of 1, 2, 6, 3, 4, 1, 4, 3, 1, and 3, 3, 1. And that's augmented matrix, right? I don't know what are going to be W1, W2, and W3, but actually we're supposed to find, like, if we can do all this, like find K1 and K2, K3, which satisfy any of these W's, right? Okay. Okay, guys, what we have, a system of equations, right? We just need to verify that this system either has a solution for any W1, W2, W3, or it doesn't have a solution for any. Maybe it has for some specific. What I'm going to do Gaussian elimination here. So my first step is going to take row number 2 minus 2 row number 1. I'm doing standard Gaussian elimination, trying to eliminate this. My next step is going to do row number 3 minus 6 row number 1. I'm going to apply just a standard technique, okay? So let's see our result. 1, 3, 4, 3, W1, and here multiplying by 2 is going to eliminate 0, right? 3 multiplied by 2 is 6, 4 minus 6 is minus 2, 4 multiplied by 2 is 8, 3 minus 8 minus 5, and 3 multiplied by 2, 6, 3 minus 6 minus 3, and W2 minus 2 W1, right? That's how we do it. And I'm going to do same over here, so it's 0 here, right? And here we have here we have 3 multiplied by 6, which is 18. 1 minus 18 minus 17. And 6 by 4, 24, minus 23. And 3 by 6, again 18, minus 17. And that's going to be W3 minus 6W1. Yeah, a little bit kind of complicated, I would say. So I've eliminated these first two coefficients. We don't really need to solve the system. We need just to show is it going to have a solution or not. So basically no one is asking us for a solution. They're asking whether it exists or not. Well, what we can do, we can divide row number 2 or multiply row number 2 by -1/2, right? Just to turn it into 1. 1, 3, 4, 3, W1, 0, 1, 5/2, 3/2, W2/2 minus or minus plus W1. Hopefully I did not miss any minuses. And, you know, I'm going to do same with row number 3 actually. Well, again, that's not a standard step, but it's going to make my life a little bit easier. 0, 1, 23/17, 1, W3/17 was minus, plus 6/17 W1. Well, why? Because it's going to be just easier for me to do next step. Next step is going to be row number 3 equals row number 3 minus row number 2, right, to eliminate this. I'm almost done. Again, let me repeat, we don't need actually to find solution. We need to show whether it has solution or not. So let's do it. 1, 3, 4, 3, W1, 0, 1, 5/2, 3/2, minus W/2 plus W1, and that's 0, 0. I'll need to subtract here. Well, I'm just going to write it down. I'm going to calculate it later, okay? 5/2. And here is going to be 1 minus 3/2 minus 1/2, right? And here's some result of subtraction. Minus W3/17 plus 6/17 W1 plus W2/2 minus W1. Wow. Okay, so guys, we are almost done. What do we have actually? We do have 1 here, we do have 1 here, and well, when we perform this operation, eventually we can turn this one into 1, right? And what we do see, we have 3 leading ones. We are going to have 1 free variable, and we can always solve it backward. And this backward solution is just going to work. So we see that like we can find the solution. So solution exists. And that's actually, I would say, infinitely many solutions, not just one solution, because we have a free variable. So after that, what we can set up? For example, we can set up K4 equals T, and then calculate K3 from it, and K2, and K1. Yeah, the calculations are going to be including these numbers, this number, and this number, and this number, because usually if somebody gives you a vector is going to consist out of some numbers, not just arbitrary W1, W2, and W3. So we see that the set spans R3. Okay. Well, that's like basically how we check it. I think what we can talk a little bit more about linear combinations. So sometimes you guys are going to have a question sounding like this. Another example. Somebody going to give you a couple of vectors. For example, vector u equals 0, minus 2, 2, and vector v equals 1, 3, minus 1. And they're asking, is vector A a linear combination of u and v? So can we represent actually vector A as k1u plus k2v? And again, to figure this out, we just need to really solve it, find out like whether the system is going to have a solution. What I'm going to do, guys, because I already know that when we do this type of solution, we are going to write down vectors as columns, and this vector A as column, I'm going to give vector A as 0, 4, 5. And I'm going to write down. So we have 0, 4, 5 equals k1, and I'm going to copy the first vector, factor u, 0, minus 2, 2, and my second vector, k2, as 1, 3, minus 1. So basically, the question is, can we find k1 and k2, which are going to satisfy or turn this equation into a true statement, or not? If we can, then A is a linear combination. If we cannot, then A is not a linear combination. Well, let's see. So what we have, if we write down like the matrix or like augmented matrix of this, we have 0, minus 2, 2, 1, 3, minus 1, and over here 0, 4, 5. That is my augmented matrix. What I see doesn't look very good to me because my first place is taken by 0. Maybe I should move second or exchange row number 1 and row number 2 to just have something non-zero in the first place, right? Minus 2, 3, and 4, 0, 1, 0, 2, minus 1, 5. Well, just to start Gaussian elimination, right? First step is going to turn this minus 2 into 1. I'm going to divide by negative 2, so that's 1, negative 3 over 2, negative 2 here. I'm going to copy the rest. 1, 2, minus 1, 0, 5. So what I did here, I took row number 1 and divided it by negative 2. Well, now what I'll need to do, eliminate row number 3. So row number 3 equals row number 3 minus 2 row number 1, right? And that's gonna be 1 minus 3 over 2 minus 2, 0, 1, 0. Sorry. Sorry guys, moved it a little bit up. And if I multiply it by 2, I'm going to get 0 here. And what I have, minus 3 over 2 by 2 is going to produce minus 3. Minus and minus are going to give me plus. So I have minus 1 plus 3, which is going to be actually 2. Sorry. 2. And minus 2 multiplied by 2 is going to give me minus 4 with a minus 4, and minus is going to be plus 4, so I'm going to get 9, I guess, right? Well, what is going to be my next step? Well, usually, guys, when we are solving problems, we almost never see that last step, but because we kind of got to that step. So what we can do here, we can eliminate the 2. And you probably already see the answer, but let's kind of do it to that last step. So I'm going to take row number 3 equals row number 3 minus 2 row number 2, just to show you what is the end of this solution. So I'm copying the first, copying the second, and now I take row number 2, 1 multiplied by 2 subtracted, I'm going to get 0 here, and if I multiply it by 2 subtracted, I'm going to get 9. Well, let's look now at this system. Guys, what do we see? We see that 0k1 plus 0k2 equals 9. If I convert equation number 3 into equation, that's a typical example of inconsistent system. No matter what are k1 and k2, it's never going to be true. We can never make it true. So inconsistent, the system inconsistent. Well, let's say usually we have consistent systems, right? But, well, this specific one is inconsistent. We cannot find this solution. So what does it mean, guys? It means that vector A is not a linear combination of these two. System is inconsistent, you see? Well, you can probably say it almost immediately like you look at the vectors. Because, well, to make it a linear combination of vectors u and v, we will need to multiply, for example, first component of u by some number, first component of v by some number, and get 0 here. But because this is already 0, no matter by what we multiply this one except 0, we're going to have a number. But if we multiply it by 0, then we are going to eliminate vector v from our linear combination and have only vector u. And we see that vector u is not the same as vector a, because just numbers are not proportional. So we cannot find a linear combination. But we kind of verified it by doing matrices, but generally speaking, you can see it from the very beginning. Okay, that's all about examples. Let's hope that we can have more in class, and I'll see you back in class.